I think we should get started. I think there's like a lot less of y'all than usual. Is it because the weather is nice? Is it nice? Or is it the usual effect of talking about rotational motion? That people get terrified and start dropping the class. I hope not. Okay, so I'm hoping it's the weather or something like that. So today I want to talk about torque and gravity and angular momentum. We'll see how far we get in doing all of this. So I guess the image here I stole from Professor Formansky, who stole it from somewhere on the internet. Has the idea that somebody wants to spend like longer with their friend, and so they're spinning to try to change, to slow down the Earth's rotation. Okay, because the Earth is rotating, it's got some angular momentum. You haven't been introduced to it yet, but you will. And if you spin the other way, in principle, you'll slow it down a little bit. But first, you got to get the direction right. So this is dangerous. You might speed up the night instead of slowing it down. And second, if you actually run the numbers, if you spin in the correct direction and do it all night, you'll convert your chemical energy into heat and slow down the Earth a little bit, so the night would get longer by 10 to the minus 21 seconds. Nobody ever said that physics is useful for this kind of thing. Okay, but this is just a joke. So let's talk about something that's less joke-like. Okay, so. A good place to get a feeling for torques is with seesaws, right? We've all seen seesaws at some point in our lives. So what's a seesaw? So it's basically a big stick, and you can sit on two ends of it, right? That's the basic mechanism. And in the middle, it's supported by something. You can balance, or not, as the case may be. So let's say we have the seesaw of the following setup. Now let me draw it on the board so I force myself to go slower. So here is an allegedly level floor. Let's say I have some support here. And what did I do? Here's a horizontal. Bear with me, please. That's the seesaw. And now I'm going to put the support right there so that this part has a length of 2r. That's what I did on the slide, right? And this part has a length of r. That's what I did up on the slide. And then there is somebody with a mass of m over here, and somebody else with a mass of 2m over there, and we're trying to figure out what's going on. And the way I drew this, you can actually look at it and see that the angle of interest is this one. Is it clear what the situation is that I have in mind? Okay. So now the question is, what is the net torque on this seesaw? Okay, so to figure this out, we need to understand the two forces that are being applied to the seesaw. So let's think about it. So first, there is a force down like this due to this person, right? So that force is 2 mg. But watch out, because that force is not purely tangential, right? Some of it is not perpendicular to the, so like, see, whatever this is, some of it is basically just pulling the seesaw that way, and it's not contributing to it rotating. The only part of this force that contributes to the rotation is the force like that. Do you buy that? So what we need to do is we need to figure out how much of this force here is this way. Okay, that's what we actually want to do now. So to get the torque, that's what we want. We want the the force, which is 2mg, times something that we have to figure out, so that this is the tangential force, times the distance that that is away from the axis, which is r, and that's going to give us the torque due to this mass. Okay, and then we can do the same thing eventually for this thing, and then add up the torques. So let's just do it one at a time and make sure we know how to do these kinds of things. And by the way, as I go, there are several ways to do every one of these problems. Some are slower, some are faster. I'm just picking one and running with it, just so you can see like an example. Okay. Well, sorry, I have to think about it for a second. So, man, geometry was always my weak point. So why am I having trouble with this? Probably that's why. I feel like I drew this in the maximally confusing way. Does my next slide do anything useful with this? Absolutely not. It just says the answer, sine theta. Oh, wonderful. Past Alexei has really screwed over current Alexei by not writing out the reasoning. Oh, man. Because apparently it was obvious to me when I wrote this, but now I'm looking at the board and I'm just melting. Okay, anybody good at geometry who wants to help? So what? I mean, obviously that seems to be the answer, but like, why in the hell? Okay, so let's try not to completely melt. Okay, so this thing right here is a 90-degree angle, right? So far, so good? Okay. So now, I would love to know, let's see. Okay, and this here is also, it needs to be a 90-degree angle. Does that make any sense? I see a lot of puzzled looks. So all I'm saying is that this is the horizontal, this is the vertical, so there's an angle of 90 degrees between them, right? And then this is the seesaw, and this is the perpendicular to the seesaw, so that's a 90-degree angle too. So this angle and that angle are the same, right? And the difference, so geometrically, right, you can see that there's this little bit here, which is theta. So this angle has to be theta. Does that make any sense so far? Or have I completely lost everybody or possibly made a mistake? If I made a mistake, please tell me if I have, okay, if you can spot it. No? Okay, I'm sorry. Geometry, sometimes I just like I have flashbacks from 9th grade geometry class. But I feel like I got it right. All right, so that's the angle theta. Good. And so now, if I know that, one minute. Okay, what am I doing wrong? Is it up in this formula? Yeah, so I suspect there might be a typo on the slide actually. So let's just go with let's try to see how far we can get on the board. You're basically saying that the slide is wrong. Probably. Let's see. Okay, so we're doing this in real time. So okay, so this side of this triangle is m or 2mg, right? And we are trying to get the hypotenuse. Does that make sense? So, okay, so let's see, this is the adjacent side. So cosine of theta is adjacent over hypotenuse. I don't like this at all. I am hoist by my own petard. I cannot do geometry, apparently. So the thing that I'm freaking out about, and I don't know if you can tell, probably you can, is that I'm about to write an equation that looks psychotic, which is 2mg over the thing that I'm looking for, the F tangential, and then derived some bizarre equation that F tangential is equal to 2mg over cosine theta. I mean, there's no way that that's correct. What did I do?
The hypotenuse should be the left leg. So basically you're...
Sorry, this being the left leg?
I think, yeah, that should be the hypotenuse, right?
Oh.
Because the force that points down, I think it's longer than the groove.
Hold on. Hold on. Thank you for your rescue. So, okay, wait. So you're saying this thing is the hypotenuse? The thing that I'm looking for?
No.
No, this is the hypotenuse.
Yeah, correct. Yeah. Like,
It doesn't look like a hypotenuse the way I drew it. So I just drew it wrong? Is that the problem? Oh my God. Yes, that's the problem. Oh. Is it? No. This is the right angle. Thank you very much. So this is, okay. Thank you. My God. Now this makes sense. So if I had drawn it correctly, I wouldn't have done something terrible. Okay, so, good. Now this line I'm looking for is the adjacent, which makes me much happier. And now all of this misleading stuff left into erasers. So the tangential force divided by 2mg, the total force of gravity, now tells me that the tangential force is 2mg cosine theta. And so what I should stick right here is cosine theta. And now you might be wondering, well, so first of all, it's clear that the way I wrote this, there's a typo on the slide, but there may be another thing that you're very confused about, among many other things. So for example, remember we had some formula that said that the torque is force distance sine theta or something, or force times radius, right? And so here there was a sine, so what is going on, right? So what's going on is you have to be careful about how angles are defined. Because for this formula, the picture is this. Here's the force. It's some vector. Here is the radius vector, just for the sake of argument. Then this is theta. Okay, but that's not the situation that we were in over here. So our theta wasn't the angle between the radius vector, which was this thing, and the gravity vector. It was theta plus 90 degrees. Do you see it? So if I try to use this formula, the theta that is here, that is the angle between the radius vector and the force. That's 90 plus theta seesaw. And what we have here is theta of the seesaw. So let me draw it more cleanly. Okay, this thing is the radius vector. This thing is the force vector. This thing right in here is theta seesaw, which we just I shouldn't say we because that's all my fault, which I just extremely painfully showed follows this equation, and you helped me not screw it up too badly, okay? Whereas the theta that appears in our standard formula for torques is not this little angle, but this angle. And there is a formula that says that sine of 90 degrees plus theta is cosine of theta. This is one of those trig identities that you may or may not remember from your long ago trig class, but is true. Okay, so you could think after all of this is all very painful, and to be honest, a lot of the pain has to do with the fact that I managed to screw up the explanation initially by drawing a bad picture and taking it too seriously. And also on typos on the slide, so I'm very sorry. This has been quite a start to a Friday class. But let's keep going for now, and then we'll get other examples that I hopefully won't screw up the explanations of. So, when the smoke clears, this is the torque due to somebody over here. Nothing is really different about the calculation over here. You get the same structure. So the torque due to the mass on the other side is going to be the mass of that person times g times the same cosine theta, but now times 2r. And the only thing to pay attention to is that this torque wants to go this way, and this torque wants to pull you that way. So the net torque is, let's see, so if I say that this way is positive, then it's the torque due to 2m minus the torque due to m. But it doesn't matter how you arrange it, as long as you put a minus sign between them, you get 0. So this is probably what you would expect, well, just 1 second, in a situation where you have two people of different masses, but they arrange themselves in the seesaw in such a way that the seesaw doesn't move anyway. Go ahead.
So with the seesaw, if one side goes down, the other has to go up. That doesn't matter.
Good. So what happened here is, how do I put this? The seesaw is, the torque is vanishing. So the net force is 0. But if you actually got into this situation, you have some speed, and you're going to keep going at that speed. But the other thing is that as you keep going, your angle is going to start changing. Let me think. Yeah, I actually think that if you have a seesaw, what this argument shows is that if you have exactly the right masses on both ends, the orientation doesn't matter. It could be like this, it could be like this, and it's still balanced. It's kind of weird, but it's true. Okay. Well, that was probably the most confusing explanation I've given in a class like this in quite a while. Just showing that, I guess if it makes you feel any better, sometimes, doesn't matter how many times you've done these problems, sometimes you screw up the geometry. We'll do our best to help make sure that happens only rarely on exams for you by helping with the geometry. Okay, so there's persistent typo of sines versus cosines here. So, moving on for a little bit. The key idea here was that radial torques, well, radial forces don't do anything. They don't contribute to the torque. Okay. And then the other thing that I just wanted to make sure have on some slide somewhere is the torque as a vector can be written as R cross F, and you can also write that as RF sine theta. That's the formula that I just had over there. And the properties of this are as follows. If theta is 0 or 180, so R is like this and F is like that, or, so they're parallel or anti-parallel. Then the sine is 0, so torque is 0. Okay, so on the other hand, if they're perpendicular, so like this or the other way, okay? Then you're guaranteed that the sine of that angle is either 1 or -1. So the magnitude of the torque is just going to be the force times the length of the radius vector. So torques are maximized when you have something perpendicular. They're minimized when you have two things that are parallel. So that is to say, they're minimized when your force is in the same direction as the radius vector. So if you have a hinge right here and you want to turn something, right? If you apply a force in the same direction, along the same direction as the vector from the hinge to the thing you're trying to rotate, okay? If you apply a force like this, it's not going to rotate. If you pull on it, it's not going to rotate. If you push on it from the side, perpendicular, it's going to rotate. And that's the best case. Does that make any sense? That's what I'm saying. Okay, so this is a chance to collect some free points, assuming the trend works for you. So I have a picture here of 3 wrenches, okay? And the question is, the wrenches are in blue, and let's say that, you know, some person who's a physics theorist doesn't actually know how to work a wrench, like me, is trying to move this wrench, and you have 3 choices for how the force is applied, like that, like that, like that. And for the sake of argument, well, yeah, you wanna loosen the bolt here, so lefty loosey. Okay. Which is the best approach? Is the question visible? Interesting. My version of Canvas thinks that it isn't visible, but okay, we'll go with it. Okay. So, well, you know, in this case, right, the radius vector is from here to there, and you're pulling this way, right? So a lot of your force is just going towards pushing on the bolt. It's not going towards pulling the thing, one way or the other. So that's not very useful. This one, I mean, yeah, it's not bad, because the angle is, you know, larger, closer to 90 degrees than it was here, but it's not as big as it could be. This is the best that it could be. So this is the case where you get the most torque. Okay. Just as a sanity check, in case you are horrified after seeing whatever just happened here, classic multiple choice problem right here from midterm 4. Okay? If you're cool with this, I'm not saying, you know, it's all roses, but like, yeah, don't be too scared. Okay. So there's too many funny symbols on this page, so I'm going to try to tell you what it says in big term, like from a faraway view first, and then dig in and tell you what's going on. So it helps to draw a picture. Imagine you have some object. So here's an object. Okay? I don't know. Maybe you're in the art department and this is some modern art piece. Okay? And it is attached to an axis here, so there's some kind of a stick that it can rotate around. And you want to know, well, something about how, like, suppose it starts like this, okay? Maybe there's a ceiling, okay, and it's attached to the ceiling by a bunch of ropes, right? And as part of some kind of performance art display, the ropes are suddenly cut, and the thing rotates down and rotates about the axis, okay? It's the art department, so, you know, weird things happen. So, so you might want to know, okay, what is the instantaneous acceleration of this object? Like somebody in the art department asked you, and you're trying to figure it out. that, I did not intend it to look quite like that. All right, whatever. So, so how would you figure this out? So the thing is, it's a little complicated because, well, I guess it kind of looks like a person, right, with a nose here. So gravity, if you look at the nose, right, gravity pulls down like that. But then, I don't know, the hand, let's say it's the hand, the gravity pulls down like that. Then there's the chin, the gravity pulls down here. I mean, basically, you know, for every one of these pieces, you have to draw a radius vector to the axis and somehow figure out how much torque there is and add up all the torques. I mean, this looks like an epic nightmare. So how do you do it? Well, that's what this slide is for. But let me just tell you the punchline before telling you like why it's true, and then we're going to use it. We're going to get examples. The torque due to gravity is okay. It's the force of gravity in magnitude. Sorry. Let me write it more correctly. It looks like that. Okay? So I'm going to tell you where this comes from in just a second. And then how to use it. So the point is that somehow this concept that we saw a little while ago about center of mass really becomes important when you're dealing with torques due to gravity. And that is a very common thing to have to think about because gravity tends to make things rotate and fall over and stuff like that. So we got to understand how it works. So basically, gravity applies a force, which is the force you know and love. Which is what is the force, right? It's mg, where m is the total mass of the whole thing. You can think of the torque due to gravity as being applied at the center of mass. So if the center of mass of this modern art representation of a person is, let's say, here, maybe that's the center of mass. Then you can figure out the torque by drawing a vector from here to there and calling it r, and drawing gravity like that. That's the force of gravity, where the force of gravity involves the mass of the entire object, and use that formula to get the torque without ever having to think about individual pieces. This is extremely powerful because you don't have to do any calculus. Otherwise, you would look at this in horror and think you're going to have to do some horrific calculus, but you don't have to. So why is it true? So let me just say it quickly because you're not really going to have to do this derivation yourselves, but it's so easy that I thought I would just show it to you. So for every piece of this object, okay, we can break it up into pieces, and we have a torque. Right? The total torque is the sum of individual torques. Well, each torque you can think of as the force of gravity on that little piece, which is mg, crossed with the radius vector, where the radius is going to the axis. Okay. Well, the gravity vector doesn't care which piece you're dealing with. You can just pull it out of the sum, and then the last thing that you can do to go from here to there is multiply and divide by the total mass. And amazingly, in the process, what comes out are two things. The total mass times g, which is the force of gravity, the simple one, not the piece-by-piece one, and this thing, which looks horrible until you remember, that's just the location of the center of mass. Nothing more than that. So, you know, there's no calculus at any point. You don't have to do anything weird. Just carefully think about what it looks like in pieces, stitch it back together, you get a simple formula. So you will not have to do this, but you will have to use that. Okay? So that's the formula we get. It's the same one that's on the board, just written in different words. Torque done by gravity acts on the center of mass. So what that means is if the object to rotate has to rotate about its center of mass for some reason, then gravity won't produce a torque. So that means that either there will be no rotation if there's no other forces, or there'll be at most constant angular velocity. So how do we think about it? Okay, I'll risk it. Okay, so imagine I have this object, its center of mass is somewhere in the center, and I balance it on my hand. So how come it's not rotating? You might think the answer is obvious. I balance it on my hand. Like, what else can happen? Well, let's think about it. Gravity is doing something complicated, pulling in every single piece. But the thing is, this object has a center of mass, which is right here. And by putting my finger under there, I just gave it an axis to rotate around, but it's located at the center of mass, which means gravity is pulling on the axis of rotation directly. So it can't do anything, because the radius vector, the distance from where gravity is applied, which is under my finger, to the place where it has to rotate is literally zero. That's why balancing works. You know, in this class, a lot of the things that we do are to figure out why things move. Sometimes it's nice that we can actually figure out why things don't move. That's our first example. So the reason balancing works is this formula. It's how balancing actually works. Okay. If, on the other hand, I were to hold this object, which is rather precious to me, so I'm not going to do the full demonstration, away from the center of mass, like around the edge, as soon as I relax one of my fingers that's holding it in place, it tries to rotate. So gravity is pulling on this point, which has a distance away from where I'm holding it. So that's why it wants to do this. Does that make sense? That's this formula in action, and that is this math in action. It's something that you know without thinking about it, but thinking about it this way brings benefits, because not only do you have the intuitive picture, you have the formulas. You can actually calculate and make very sharp predictions about what's actually going on. Okay. So, what I want to work through is a really fun example. It's fun because having worked through it, I get to show you a video. And I think the video is quite fun. So, okay. Suppose I have a stick, okay, and there's a hinge point right there. And initially the stick is held in place, and then it's let go, and it falls. And so the question is, how fast does the end of the stick fall? That is, what's its acceleration? Okay? So let's try to understand that using the ideas that we just met. Okay. Here's flat ground. Here's a stick. Here's an axis of rotation. Let's say the stick is uniform. So let's put a coordinate system on the problem. This is the angle theta. The length of the stick is L. What else did I have in this picture? Well, there's a force of gravity. The center of mass of the object is right there, right? If it's uniform. Where else can it be? So gravity, well, I didn't draw it, right? Maybe right there. So gravity pulls straight down from that point. Right? That's the force of gravity, which is mg. And finally, if you really want to draw all the forces, there's also some kind of force coming from the hinge, right? Which is going to kind of go, I don't know, like that or something. Force hinge. It's pushing into the ground, so it's pushing into the ground is pushing back, that's the force from the hinge. Okay, so those are all the forces. So now we're trying to figure out, like, how does this thing move? And there are only two forces. There's gravity and there's the hinge force. So the torque due to the hinge is nice and easy. It's applied at the axis of rotation. Therefore, it's zero. Because it's always radius times force, but the radius is zero, because it's the radius, the distance from the axis that you care about. Okay, so not to worry about that one. The torque due to gravity. Okay. So for that one, we have this vector and this vector. And the angle between these vectors is that thing, right? Let's call it alpha. You see that? So the formula says this is force of gravity times the length of this vector, which is L over 2, times the sine of the angle between the two vectors. Okay? So this is mg, L over 2. Okay, so let's now think about it, right? So, can I write alpha in terms of theta? So yes, because this is a right angle. So alpha is 90 minus theta or something like that. And there's a nice formula that says that sine of 90 minus theta is cosine of theta. So as it happens, this can be written like that. Cosine of theta. Okay, there we go. We got the torque. Okay, now you may be wondering, who cares? Well, okay, we got the torque. So now the thing starts falling. So we can ask, well, how does it fall? Well, the torque, which is over here, is equal to the moment of inertia times the angular acceleration. We're going to have to figure out the moment of inertia in a second. But the angular acceleration, alpha, can be related to the acceleration of the end like that. And go back to circular motion, right? The angular acceleration is it just has units of 1 over second squared. And normal acceleration has units of meters per second squared, so you gotta get rid of the meters somehow. So you have to divide by the length. So the angular acceleration is whatever it is, but the actual acceleration gets bigger and bigger as you go out this way. Okay, so if we want to know the acceleration of the end, then we're gonna need this. Okay, so what else do we need? We need the moment of inertia. So the moment of inertia is the moment of inertia of a stick around its endpoint. Right? It's this kind of moment of inertia. This is something that you would look up, okay? And I know the answer here because we've done it recently, and so I still happen to remember. This happens to be the answer, but you would either look it up or get it from the parallel access theorem or something like that. So now we can put everything together. So let's do that. I'll do it over here. Okay, so the torque is on the one hand, mg, L over 2, cosine of, cosine of theta, sorry, cosine of theta. And on the other hand, that is equal to the moment of inertia times the acceleration of the endpoint divided by L. And I want to know the acceleration of the endpoint. Yeah? So the first thing that I notice is that the m's drop out. The next thing is I can divide both sides by L. then I get rid of this. On the other side, the L downstairs becomes L squared. Okay, so this is getting, I don't want to do many things in one step, so let's just collect what we have. We have a half G cosine theta is equal to a third. This cancels that, so A and. Did I do something else? Yes, go ahead.
Never mind.
Yes?
Would you divide, the ML squared, so
Let's check. Let's check. I may have done one too many things in one step, so let's try it again. So let me do it one step at a time, and then we see if I made a typo. Thank you for keeping me honest. So first I'm going to copy down one of the things here. mg L over 2 cosine theta. And over there I'm going to do mL squared. The acceleration of the endpoint divided by L. So far so good? I just copied. Okay. So on this side, it's 1/3 mL times the acceleration of the endpoint. On this side, I have mg 1/2 L cosine theta. The powers of L on both sides match, so the L's cancel. Yeah? So the L's cancel. The powers of M on both sides match, so the M's cancel. So the equation that's left over is a half G cosine theta. Okay. So far so good? And then we multiply both sides by 3, and we get the acceleration of the endpoint. 3/2 G cosine theta. Okay. That's interesting. It's interesting for the following reason. If theta is small, cosine is very close to 1, right? So that means that when theta is small, this is very close to 3/2 of G. Did you see that? So that means the end of the stick is accelerating faster than the acceleration of gravity when the stick has almost hit the ground. So this is very funny. It's a falling object that's falling faster than the acceleration of gravity, but it's happening because of weird rotational things. But let's see if it's really true. To the extent that, YouTube is true. So this is all the same stuff, you're just going to see it on Canvas. Okay, so this is a case where YouTube doesn't lie, but this is very hard to see in real time because it happens extremely fast. So I'm just going to play the video, crossing fingers that the video actually works. You never know. So let's try. Same setup, okay, and what's going to happen? I should probably tell you like what you're about to see. So this person is going to very slowly and dramatically remove the stick. Then this thing is going to start falling. And this ball is going to end up in the cup. Now, why is that interesting? Well, for that to happen, right, the ball is just going to fall, like normally. Whereas the stick is going to do this weird motion that we're talking about. So for the ball to end up in the cup, the stick has to beat the ball on the way down. So let's see. I don't know who Nils is.
Roland and action.
This is why I didn't do this demo in person. It's completely boring. But if you can see it slowed down, you can see the stick wins in plenty of time. That's this formula in action. Yes?
How does this connect to kinetic energy? Because kinetic energy is mass times velocity squared. What happens to mass times velocity squared? And since it is going faster.
Good. So there are several things happening here, which is that there is rotational motion as well. So, it all has to be consistent. It's just that our intuition for how things can accelerate due to gravity, they work fine if things are just falling, right? But here, it's not just falling, it's also rotating, and that screws up our intuition. So I have to say, this is not a case where I have amazing intuition from like in some deep cosmic sense, like why is it true? Maybe one can figure it out, but I don't have a quick story for you. But this is just to say that you gotta be careful with saying that everything falls in G. Free objects, like objects that are free to move however they want, fall in G. Things that are like rotating as they fall, well, it could get complicated. Okay, roughly speaking, because some of the energy that's coming from the change in height can also be traded off against rotation in a weird way, and that can lead to an apparent acceleration faster. So if you were to track some other, well, yeah, maybe let me stop with that. Yeah. Okay. So the last thing that I want to begin talking about today, and we'll talk more about it on Monday, so I still have a few minutes, let me try, is angular momentum, just so that you've heard the concept exists, okay? So we've had many analogs for normal, like linear motion things with rotational motion, and momentum is a useful thing, normally, and there's an angular causa limit, which is angular momentum. Okay, so what is it? Well, the angular momentum is called L. People were running out of letters by the time they named it. And it is rotational mass, that is to say moment of inertia I, times the angular velocity, the rotational velocity, which is omega. Okay. How do we unpack this formula? Well, okay, so it's I times omega. So let's just do it for a point particle, right? So what's the angular momentum of a point particle? It's got to be I times omega, because I said that was the formula. But for a point particle, the angular momentum, the moment of inertia, I misspoke. The moment of inertia is omega r squared. And if you write out the, okay, there's such a horrific typo on this slide that, let me do it on the board. Okay, so there's some typos here, so I'm gonna do it right. Okay, so this thing is mr squared. And then omega times r is v. So v over r is omega. Yeah? And so what we're getting is mvr. And what is this? This is momentum times r. You see it? So there's a nice, there's a very common thing that angular things and linear things are related by some power of r, either upstairs or downstairs. This is no different. And my final punchline here was correct, but some intermediate step was psychotically wrong, because it was supposed to be, what was I doing? Oh no, was it correct? It was correct. Oh boy, today is not my day. Okay, I just, algebra just completely escapes me today, and geometry, and physics, and math. Okay, so I think on that note, I should declare victory before I do anything else that's stupid. So thank you for bearing with me. I'll do better on